Hey guys, Mr. Betts here. Let's take a look at some examples where we're going to use these Riemann sum approximation methods. So we're going to use all four of them. We're going to use RRAM, LRAM, MRAM, and TAM. And I'm going to do it with different numbers of intervals for each one so we can kind of see how the math works out with each one and the process works. So in all of them, we're going to be using the same function. We're going to be using the function f of x equals x squared plus 1. And we're going to approximate the integral from 1 to 3 of f of x dx. So just real quick, before we get into the examples, a reminder of what we're trying to do, what we're trying to accomplish here. If we were to graph this function, x squared plus 1, it's going to be a parabola, opens up with a y-intercept of 1. We want to know what is the area between that curve and the x-axis between x equals 1 and x equals 3. So we're going to have on our graph the point 1 comma 2. If you just plug 1 in for x, you get 2 for y. We're also going to have the point 3 comma 10 here, but what we're ultimately trying to find is this area right here. And later on, we're going to figure out a process to find that area exactly. But right now, we're going to look at numerical processes where we can approximate that. Okay, so again, we're going to go through each one. And the first one, we're going to use a right Riemann sum, which is what I abbreviate as RRAM. So actually, I'm going to leave that picture up here because I want to look at what that picture is going to look like. I won't necessarily use the picture for all of them, but to use this right rectangular approximation method, first of all, we're going to use 4 rectangles of equal width. So one of the first things we need to do is figure out how wide our intervals are going to be. And we're going to use delta x for the width of each subinterval. And to find that width, essentially we need to know what is the width of the entire interval. And that's going to be the width of the entire interval. If this is a and b, we would find that width by doing b minus a. And then we're going to divide it by the number of subintervals because they are equal in width. So if we're going from 1 to 3, then we're going to use 4 subintervals. And so if we divide that evenly, delta x is going to equal 3 minus 1 over 4. So to generalize that formula, delta x is going to equal b minus a over n. This is something that we're going to see not only for this, but for some other things that we're going to do in the future. And it essentially just tells us how wide each subinterval should be to get a certain number of subintervals of equal width. So in this case, each subinterval is going to have a width of 1/2. So when I'm making these rectangles here, let me just draw the heights of them. The width of each one of these right here is going to be 1/2. All right, now the other thing we need to do to approximate with our right rectangular approximation method is figure out how tall the rectangles are. So to find the area of each individual rectangle, we're going to do the width times the height. And to get the height, we're going to be using the values of the function. And specifically, we're going to use the values of the function at the right endpoint. So at the right endpoint, in the first subinterval, we're going to be using the height of the rectangle right here. So our rectangle is going to look like this. In order to get that, I need to know what this x-coordinate is right here so that I can plug that into the function to get the y-coordinate and the height. So that x-coordinate is going to be 1 plus the width of the interval. So it's going to be 1 plus 1/2 or 3/2. And essentially what I'm going to do to get each x-coordinate here is I'm going to keep adding 1/2. So we're going to have 4 halves or 2, then we're going to have 5 halves, and then we have 6 halves or 3, which is our right endpoint. So by adding 1/2 repeatedly, eventually we're going to get to the right endpoint after 4 subintervals. So the height then here, I'm going to change color. I know I got a lot going on here, but this height right there is going to be f of 3/2. So we're plugging the 3/2 into f of x to get the y-coordinate of that point right there, and that's the height of that rectangle. So to find the area of the first rectangle, we're going to do the width of the rectangle, which is 1/2, times the height of the rectangle, which is f of 3/2. Now, Normally, I would write the actual value of f of 3 halves here, but for the purpose of just following the work in this first example, I'm going to leave it as f of 3 halves to start with. Okay, so that's the first rectangle. Then the second rectangle, since we're using 4 rectangles, we're going to have 4 of these. The second rectangle has the same width, which is 1/2, and then the height, sorry, I zoomed in so you can't see the picture there. The height is going to be the value of the function at this point. Okay, so we're going to have this rectangle, so that's going to be f of 2. Then we're going to have, for our third rectangle, we're going to be using this point here, so the height times the width. So width is 1/2, and then the height is going to be f of 5 halves. And then for the last rectangle, the width is still 1/2, and then the height is going to be f of 3. Okay, so a couple of things I want to do here before I move on. First of all, I want to identify this. So I don't want to generally have work here without saying what that work is. So I'm going to identify that just by saying RRAM, and I'm going to use a subscript 4 here to show that's the right rectangular approximation method with 4 rectangles. If we look at just kind of the general form here, notice that each rectangle, since the widths are equal, has a width of 1/2. That 1/2, just to simplify the process for us, we can factor that out because it's in each term. So when I rewrite this here, I'm going to factor that 1/2 out, and then the heights of the rectangles are going to be the values of those functions. So f of 3 halves is going to be 3 halves squared plus 1. So 9/4 plus 1 is 13/4. F of 2 is going to be 2 squared plus 1, which is 5. F of 5 halves is going to be 5 halves squared, 25/4, plus 1 is 29/4. Oh, and then we got one more. F of 3 is going to be 3 squared, which is 9, plus 1 is 10. So what we end up with on the inside there is going to end up being 51/2, and we multiply that by 1/2 that we factored out, and that's going to be 51/4. And that's enough here for what we need to show. In fact, if this were a free response question, this answer right here would be okay. Nothing wrong with stopping at that point because we have a numerical answer that's equivalent to the final answer, so we can stop. I did want to simplify here, though, because later on I'm going to compare this to the actual value of this area. For now, let's answer one final question here, and that is this an over or an under approximation? By looking at the graph here, I think it's pretty easy to see that the rectangles have a little bit too much area, a little bit more than we wanted, so it's going to be an over approximation. It does ask us to explain why. So just saying that the rectangles are too big is not a good enough explanation. So this is going to be an over approximation. And then because, so the reason that it's an over approximation is because we're using the right endpoints, and the right endpoints are higher than the left endpoints and every value in between because the function itself is increasing. So I'm going to say because f of x is increasing. Okay, and specifically it's increasing on this interval. F of x is not always an increasing function. Over here, as we go to the left, it is a decreasing function. But on this interval, f of x is increasing. And remember, we know increasing functions are going to have an over approximation for RRAM on that interval. Okay, moving on. I'm going to go through the rest of them quite a bit more quickly. But we're going to kind of mix things up. So instead of RRAM, now we're using left endpoints, and we're going to use 5 rectangles. So I'm going to do a quick sketch here. I think a sketch is usually helpful. We're going from 1 to 3. And I'm going to start here by finding the width of each interval. So delta x is going to be, so the width of the entire interval is still 3 minus 1, but this time we're dividing it into 5 subintervals, so it's going to be 3 minus 1 over 5. So each subinterval is going to have a width of 2/5. So figuring out what those x coordinates are going to be along the x-axis here, splitting into 5 subintervals, we're going to have 1 plus 2/5, which is 7/5. And then plus another 2/5 is 9/5. Plus another 2/5 is 11/5. Then 13/5. And we add 2/5 one more time, we're going to get 15/5 or 3, which does get us to the right endpoint. So now moving 5 times by this delta x value here, we get to the right endpoint. So the widths of each of these rectangles is going to be 2/5. And now to approximate here, we want to multiply the width times the height. And the heights now we're getting from the left endpoints. So for our first subinterval, let me identify the work that I'm going to write here. So LRAM 5 is going to be 2/5 is the width times the height. So it's going to be f of 1, but I'm going to skip the step of writing f of 1 and actually evaluate f of 1. So f of 1 is going to be 1 squared plus 1, which is 2. So that's the area of the first rectangle. Then the second rectangle, we're going to have the same height, or I'm sorry, the same width. In fact, we're going to have that width of 2/5 for all of them. So I'm going to factor the 2/5 out. So this is the height of all of the rectangles. Sorry, I keep saying height. This is the width of all of the rectangles. And in the parentheses here, I'm going to have the heights. And again, since all of the widths are the same, we can factor that out. So then we're going to have the width times f of 7/5. So f of 7/5 is going to be 7/5 squared, 49/5, plus 1 is 54/5. All right, and that's giving us the area of this rectangle right here using the left endpoint. Then we're going to have the width times the height for this rectangle. That's going to be 9/5 squared, 81. Sorry, this is 20/5. 81 20/5. I messed that one up. Sorry, 49 20/5 plus 1 is going to be 74 20/5. Then we're going to have 81 20/5 plus 1 is going to be plus 104 20/5. Then we're going to have 11/5 squared is 121 20/5 plus 25 20/5 is 146 20/5. And then our last rectangle here, we're using the 13/5. So that's 169 20/5 plus 25 20/5 is 194 over 25. Okay, so again, width times height. And so really we're multiplying that width times each of those heights because we're distributing, but we factored that out. And we are just going to simplify this. So 2/5 times all of that is going to give us 228 over 25, which as a decimal is 9.12, but I like fractions better. Really doesn't matter as long as it's equivalent. If this is a non-calculator question, which I'm assuming this is, first of all, this is sufficient. You could stop there. But for the purpose of comparing to the other approximations, I like that 9.12 or the fraction here. Last thing is we want to answer the question, is it over or under? This time, since we're using left endpoints and the function is increasing, the left endpoint is going to be below the rest of the points on each subinterval. So this is going to be an under approximation. And the reasoning is the same as we gave for the over approximation on the last example. It's because f of x is increasing. So I'm going to say the function because it's not actually identified as f of x. So the function is increasing. So when we have an increasing function, the left endpoints are going to be the lowest on each subinterval. The right endpoints are going to be the highest. So LRAM is going to be an under approximation. RM is going to be an over. Okay, next one we're going to use MRAM. So midpoints with 3 rectangles of each equal width. So again, I'll start with a quick sketch here. It doesn't have to be perfect, but kind of give me an idea. So we're going from 1 to 3. And we're going to use 3 subintervals. So we're splitting it up into 3 equal parts. So delta x is going to be, so width of the entire interval, 3 minus 1, divided by the number of subintervals, and that's going to be 2/3. So finding the x-coordinates then for the endpoints of our subintervals, we're going to do 1 plus 2/3 is 5/3, plus 2/3 is 7/3, plus 2 more thirds gives us the 3 at the end. Now, the tricky part here with MRAM is going to be the heights of the function. We're not using, on the first subinterval, we're not using the left endpoint, we're not using the right endpoint, but we're using the point halfway between those two. And so we also need, in addition to the x-coordinates I have labeled here, I need the x-coordinates of our midpoints. So I'm going to do that in a color that's a little more obvious to see here. So halfway between 1 and 5/3 is going to be 4/3. Halfway between 5/3 and 7/3 is 6/3, or 2. And halfway between 7/3 and 3 is going to be 8/3. So we're actually using the heights at these points to get the heights of our rectangles, and then the widths are going to be the delta x that we were using before. So our midpoint approximation with 3 rectangles, the width of each rectangle is going to be 2/3, so I'm going to put that first and factor that out. Then the heights are going to be, and I'm going to go back to the function notation here for this problem just to really emphasize where we're getting the heights here. So we plug the 4/3 into the function to get the height here. Then we're going to plug the 2 into the function to get the height here. And then plug the 8/3 into the function to get the height here. So just doing a little evaluation here. We're going to have 4/3 squared plus 1 plus 2 squared plus 1 plus 8/3 squared plus 1. So this is f of 4/3, f of 2, and f of 8/3. And that simplifies to give us 286 over 27. Now, just like the other ones, I asked the question also, is it an over approximation or under approximation? This one's a little bit trickier to answer here because if you look at each subinterval, I'm going to choose the last one here, we have a little bit too much for part of it and we have a little bit too little for part of it. And we don't really know without further analysis how those balance each other out. It does turn out that the over part here is slightly bigger than the under part there. That's the case because this function's concave up, but that's requiring more analysis than we have to do. We actually don't have to answer this question for midpoint approximations. Okay, so I left it on here because I did want to talk about it, but when we're doing midpoint approximations, we're not going to worry about whether it's an over approximation or under approximation. We will see later whether it is over or under, but that's when we compare it to the actual value. Okay, one last one here with our analytic approach to these approximation methods. This time we're doing the trapezoid approximation method, and we're going to do it with 2 trapezoids. So going from 1 to 3, and so the width of each interval is going to be 3 minus 1 over 2, because we're going to do 2 equal subintervals. So the width of each interval is just going to be 1. And so that's going to give us a nice easy one here. That's going to be at 2. So our trapezoids now are going to look like this. We're going to have 2 sides there. We're going to connect that with a straight line, and we're going to use the x-axis. So the height at the left endpoint is going to be f of 1. The height at the left or the right endpoint is going to be f of 2. So as far as finding the area of a trapezoid goes, these are the bases. So remember, to find the area of a trapezoid, we're going to average the bases and then multiply by the height. And the height for the trapezoid is going to be actually the width of the interval. So our trapezoid approximation with 2 trapezoids is going to be the average of the bases, f of 1 plus f of 2 divided by 2 times the height of the trapezoid, which is going to be the width of the interval, which is 1. And then we're going to end up we're going to be multiplying by 1 for the second trapezoid also. So for this one, we're looking at that trapezoid. So it's going to be f of 2 plus f of 3 over 2. And so just plugging in that'll work. We have 1 times, so f of 1 is 2, f of 2 is 5, f of 3 is 10. So we get 7 halves plus 15 halves is 22 halves, which is 11. So our trapezoid approximation method with 2 trapezoids is going to be 11. We should be able to answer this question of whether it's an over approximation or under approximation. I really tried to emphasize it when I drew the picture here, but notice that when we draw the trapezoids, they're a little bit above the function. And the reason that they're above the function is not this time because it's increasing, but it's because the curve is curving in an upward direction. It's concave up. So our trapezoids are going to be an over approximation. But when we are using trapezoids, we're not looking at increasing and decreasing, but we're looking at concave up or concave down. So because function is concave up. So because the function is concave up, the straight lines that we're using to get the tops of the trapezoids are above the function, and that means that our areas are a little bit too big and we get an over approximation. Okay, so we approximated the same integral in 4 different ways. I want to look at all those answers in one place here, along with the actual area. So if we were to actually find the area that we're approximating right now, this actual area is going to be 10 and 2/3. If we look at the answers that we got here, they're all in the same neighborhood of that 10 and 2/3, some a little closer than others. But notice that RRAM is a little bit too big, LRAM is a little bit too small. It does turn out that MRAM is a little bit too small, and the trapezoids are a little bit too big. So we predicted all of that based on features of the graph that we knew. We also used different numbers of subintervals, so it's hard to compare which ones are better or worse for this particular function. I will say that it's going to vary from function to function, whether RRAM, LRAM, MRAM, TAM is better. Trapezoids do tend to be the best, but that's not always the case. You can see here, though, that with just 2 trapezoids, we've got an answer here that's within 1/3, and it is the second closest one. MRAM's just a little bit closer, but it is a good approximation with just 2 trapezoids. I will say moving forward, though, and trying to make our approximations more accurate, RRAM tends to be the easiest one to generalize, so that's the one we're going to kind of focus on moving forward, but you should have a working knowledge of how all of these work.